Candace, I have a question.
Yeah, what's up?
Is decomposition a physical or a chemical change?
Chemical change. Anytime you need to write it as a chemical reaction, it's a chemical change, okay?
No, I meant like of an of a fruit or a dead animal.
Oh, you mean like
Yeah, like actually.
Yeah, that's definitely a chemical reaction.
Is it just reacting with like oxygen, or how is?
Yeah, there's a bunch of different things that are going on in that. And you would probably be better suited to asking a biology teacher some of that stuff. But yes, that is definitely a chemical reaction. What you end up with at the end is not what you started with. Okay, so welcome everybody. It's like so chilly today. I'm all bundled up. It's amazing how like 55 degrees on the fall side will feel so cold, but then on the spring side, it's like super warm and you're out in a bikini. Yeah, so already starting to bundle up again. Okay, we're gonna keep working, chipping away at chapter 3. So we left off, we were talking about molecular weight and how we can pull that information just off of a periodic chart, which make sure I've got a periodic chart available. And so we're looking at how the formula weight is the same thing or is equivalent to the molar mass. And molar mass is just it's in units of grams per mole instead of AMUs. And this is useful as a conversion factor, going from grams to moles or moles to grams. So when I write something like I have 58 grams per mole of NaCl. That is its molar mass, also its atomic mass. Another way to write that is to say that I have 58 grams of NaCl for every 1 mole of NaCl, or we could flip that and say, hey, 1 mole of NaCl for every 58 grams of NaCl. The 1 will always stick with the mole. So now we've got grams and moles. Ooh, it's blowing me up right now. We've got grams and moles. So we can use that as a conversion factor to go from grams to moles or moles to grams. So somewhere you want to have this flow chart available for you. So in the middle, you want to have moles, and sometimes we call moles the bridge or like the crossroads in chemistry, because the mole sits in the center of this flow chart. And we're good over here. So formula units is another way of saying atom or molecule. All right, so atom or molecule. So in order to go from moles to formula units or atom/molecule, we've been using Avogadro's number. Now, if I want to go from moles into grams, so this is another part of the flow chart, or grams to moles, I use the molar mass to convert between those two. There is no fast way to go from grams directly into molecules, okay? You're always going to have to take a two-step leapfrog process. You'll have to hop into moles, and then from there you'll get to hop into formula units. So if we look down here, this says, hey, how many atoms are in 3 grams of copper? So you're starting, when looking at this flow chart, we are starting with grams. So we're starting over here, and we want to end up with atoms all the way over here. So we need to take 2 hops. The first hop is to go from grams of whatever I'm dealing with, in this case it's copper, into moles of copper. And the way I do that is use the molar mass. So I've got 3 grams of copper, and 1 mole of copper is equal to 63.5 grams. This number did not come out of thin air. Look at the molar mass on the periodic chart. The molar mass for copper is in fact 63.54. One thing that I'll see students do sometimes is they'll use the atomic number. That's the number of protons, so don't use that. Use the atomic mass. All right, and in this case, they took their value and they not working for me right now. So again, this number is coming from the periodic chart. If instead of it being copper, they had said something like silver or oxygen, you would need to use the molar mass of those. So this part is not dependent on what the material is, right? Because we know Avogadro's number is always 6.022 times 10 to the 23rd. So this isn't dependent on the material. This is dependent on the material. So you have to take into account what you're looking at. So we take our grams of copper and we're going to divide it by the molar mass. Now, I don't think about it, oh, I'm going from grams to moles, I have to divide, or if I'm going from moles to grams, I have to multiply. I just set it up in such a way that the units will cancel. This is a little bit confusing, but this sort of should sit right here. Okay, so 1 mole of Cu over 63.5 grams of Cu. Let me just write it underneath. 1 mole of Cu over 63.5 grams. Why did they put the grams on the bottom? Because what happens is grams will cancel. And now we've hopped into units of moles of copper. So what we've done is gone from here to here. We don't use Avogadro's number just yet. In this first step, we just use molar mass. Next step then is to go from moles into the formula unit. That's where we use Avogadro's number. Since moles are on the top, I need to put the 1 mole on the bottom, and then we can put Avogadro's number on top. The mole unit will cancel with the mole unit, and we'll be left with units of just atoms. So have this written down somewhere. Then actually, I'm going to pull up the guided notes because these slides really only give us one example, which is definitely not enough for this. Okay. And actually, in the notes, there is a little spot that says moles is a bridge for the calculation, so we can even, I can write that in there now. So we'll put moles in the center. I'm going to put grams over here. I'm going to put formula unit over here. So in order to flip-flop between these two, I use Avo's number. In order to flip-flop between here and here, I use molar mass. So let's do a real simple one right here. What is the mass in grams of 4.5 moles of potassium? So I have 4.50 moles of potassium. I want to get this into grams. So if I want to get into grams, I'm going to put the gram on the top. I'm going to put the mole on the bottom. Why? So that the moles cancel. The mole always gets the value of 1. The gram is going to be the mass, right? So for potassium, 39.1 is close enough for that. 39.1. Okay. And you may want to start to get into the habit. Oh, come on. Sorry, my pen is giving me a hard time. You might want to start to get into the habit of putting it as grams of potassium and moles of potassium, because a little later in the chapter, we're going to have moles of both of them. So moles will cancel here, and you should be left with roughly 176 grams. And 76 grams. So second one here is going in the other direction. We're given grams, right? We're given that we have 78.9 grams of calcium. And we want to find moles of calcium. So start with our given, 78.9 grams. Gram needs to go on the bottom, mole needs to go on the top, and it's specifically moles of calcium, grams of calcium. The mole gets the 1 value, the gram gets the numerical value. So in this case, calcium has a mass of roughly 40.1, okay, or 40.08. So in this case, I will take my value and divide it by the molar mass. We'll be left with moles, and we should get 1.97 moles of calcium. I want you to do number 3. The only difference with number 3 than the first two is that this is a compound, okay? So you're gonna have to do a little extra legwork on your molar mass. So go ahead and try and set that one up using dimensional analysis. I think when we put it in dimensional analysis, it is the cleanest way. It's the best way to get the right answer every single time. So we've got 508 grams of NaHCO3, or sodium bicarbonate. And actually, while you're at it, do 3 and also do 4, because it's the same thing going in the other direction. And again, if you have a question while you're working on it, feel free to either throw it in the chat or you can just unmute yourself and ask. All right, so for the first one, how many moles of sodium bicarbonate are in 508 grams of sodium bicarbonate? So we start with our given information always. 508 grams of this NaHCO3. So if they hadn't given you this, right, and instead they gave you this, sodium bicarbonate, you would need to be able to write the correct formula. If you can't write the correct formula, then you can't get the correct molar mass. If you can't get the correct molar mass, then you can't get the correct answer on how many moles it is. So the things start to piggyback on top of each other. So in this case, grams is on the top here. So I'm going to put grams of the NaHCO3 on the bottom. And I'm going to put the mole on the top. 1, 2, let's see, what did we get for our sodium bicarbonate has a molar mass of 84.01, 84.01. Grams of it will cancel and we'll be left with moles, and we should end up with 6.05 moles of the NaHCO3. If we go the other direction, 6.33 moles of the NaHCO3. Use our conversion factor, which is our molar mass. It's the same conversion factor as the previous problem. We just need to flip it, right? Because moles is on the top here, so I need to put my mole on the bottom. And then on the top is where I'm going to put the 84.01 grams, the NaHCO3. The moles will cancel and you'll be left with just units of grams, 532 grams of your NaHCO3. Sorry, it's a little tricky to write. Doesn't want to write on there. The compound name. Okay. So any questions on those setups? It's always that same setup. If you're going from grams to moles or moles to grams, it's always going to be using the molar mass. I want you to do number 5 and number 6. These are two-steppers, okay? And it's giving you an extra little challenge by saying, hey, it's nitric acid. So you need to know what nitric acid is or look it up. But this is a two-stepper, so we're gonna go, first one is molecules. I wanna know grams. Second one is talking about water, and it gives you molecules, and I want mass. This one gives you mass, and I want molecules. I'll give you all maybe 5 minutes to set that up. All right, so first you need to figure out what nitric acid is, which is nitric. So ic comes from 8. So it would be nitrate with a hydrogen. All right, so it is, we have 4.20 grams of HNO3. First thing I got to do is get it into moles. So gram will go on the bottom, mole of the the HNO3 will go on the top. Grams of the HNO3 on the top. So the molar mass of our HNO3 is 63.02. So 63.02 will go on the bottom and the 1 mole will go on the top. Next step is to go from, so we can say goodbye to our grams. Next thing is to get moles out of the way. So I'll put mole on the bottom and I want to get into molecules. Molecule of HNO3, HNO3. Again, the mole gets the value of 1. Up top, we're going to put that 6.022 times 10 to the 23rd. There goes moles. And the only unit that I have left will be the molecule. It should be a big number. We would expect to have a lot of molecules. 4.01 times 10 to the 22nd. HNO3 molecules. All right, go in the other direction. 2.50 times 10 to the 25th water molecules, so H2O molecules. We're just sort of going from this side back that way. So again, I still have to go to moles first. So moles of H2O on the top, 1 mole will always be equal to 6.022 times 10 to the 23rd H2O molecules. Then I want to get it into grams. So for every 1 mole of H2O, I am approximately 18 grams. Molecules will cancel, moles will cancel, and we're left with grams, specifically 748 grams of H2O. Any questions on that? I want that to feel relatively easy. And if it doesn't, ask me. But definitely your next test or your test for this chapter, it's only going to be over chapter 3. It's going to be on Sunday. So I would have a formula sheet or something with like all these little flow charts in there. And the most difficult thing will probably just be which one do I need to be using when. So moving on, we're going to talk about empirical formulas and how to determine empirical formula. So actually, we go back. We had this opportunity here to go over percent composition already, and you were able to figure out what the percent is by taking the mass of the individual element and dividing it by the compound's total and multiplying it by 100. That one was really easy to do. What we're going to do now is I'm going to give you the mass percents, and I want you to figure out the compound. It takes a couple more steps than just dividing by the total and multiplying by 100. So specifically, the flow chart is going to look like this. So I'll give you the mass of the elements, or I'll give you, so I'll either give you this, the mass of the elements, or I'll give you the mass percent of the elements. If I give you the mass percent of the elements, that's going to be like, hey, it's 33% this, it's 12% this. You can just assume it's a 100-gram sample and take that percent and flip it to a gram unit. Okay? So if you're not given grams already, you're given mass percent, just convert it to grams by changing the unit to gram. After that, what we want to do is use the molar mass for each of the individual elements that we have and convert from grams of each element into moles of each element. Then once we have the moles of each element, we're we're going to figure out the molar ratio, because usually this number right here comes out as being a decimal. So the ratios are correct, but we need it to be in whole numbers. So we will divide by the smallest guy, maybe multiply by a factor to get the empirical formula. I think this will make more sense after doing an example. So let's look right here. So we've got a compound para-amniobenzoic acid, PABA. That's what you see on a bottle. So these are its compositions. So carbon 61.31, hydrogen 5.4%, and nitrogen 10.21%, and oxygen 23.33%. So first things first is that each of these is given in percentage. So I can assume a 100-gram sample and just convert each of those into grams. So I like to write them out kind of stacked. So carbon, I have 61.31 grams of carbon. I have 5.14 grams of hydrogen. I have 10.21 grams of nitrogen. And I have 23.33 grams of oxygen. So if we're going to write a chemical formula, remember a chemical formula is telling you how many atoms you have of each, or it's telling you how many moles you have of each. It's not a mass relationship, right? So when I have something like H2O, I'm not saying I have 2 grams of hydrogen for every 1 gram of oxygen. I'm saying I have 2 atoms of hydrogen for every 1 atom of oxygen, and those atoms weigh different amounts. So we want to get out of grams and we want to convert into the moles of each of these guys. So you take the molar mass of carbon, the molar mass of hydrogen, nitrogen, and oxygen. The slides do that already. Okay, so in this case, we've got our carbon grams. We're going to divide it by the molar mass, so the grams cancel, and we end up with moles of carbon. We do the same thing for hydrogen, but obviously we want to use the molar mass of hydrogen. We don't want to use the molar mass of carbon. We take it for nitrogen as well, using the molar mass of just 1 nitrogen. And then we do it for oxygen. So now I know my relationship of moles. Sometimes people will write out what's called like a skeletal chemical formula. So they'll take carbon and they'll put the subscript of 5.105, hydrogen with a subscript of 5.09, nitrogen with the subscript of 0.7288, and oxygen with the subscript of 1.456. Because this ratio, it's a correct ratio, but why don't we like it? We don't like it because it's not in whole numbers. We can't have 1.456 atoms. So we need to get this into whole numbers. And the best way to do that is to divide by the smallest decimal. So in this case, it would be the 0.7288. So every single thing is going to get divided by whatever the smallest decimal is, 0.7288. You don't have to write it like this. You can just go over here and divide each of these by this guy here, 0.7288. Why the smallest one? Because it just is the easiest, fastest way to make it happen. So what we end up getting is that carbon, when we divide our original number by that 0.7288, it gives us 7.005. All right, this is close enough to 7 to call it 7. If you got something like this, let's say instead of 7, you got like 7.33, that would not be close enough, okay? So you wouldn't be able to just round that to 7. But if you're, if it's smaller than like a 1/10, you can definitely round it. So we've got a 7 here, we've got a 7 here. Anything divided by itself is 1. And then when we took this 1.458 and divided it by the smallest number, we got something relatively close to 2. So then from there, you just write the formula. So carbon is going to have a subscript of 7. Hydrogen is going to have a subscript of 7. Nitrogen is going to have a subscript of 1. And oxygen is going to have a subscript of 2. You can ditch the 1. So there we go. C7H7NO2. So a little bit more work than the other way. So take your percent, go into grams, from grams go to moles, divide by the smallest. Hope you get whole numbers. That'll be your formula. So let's do another example of this. Here. This one is the one we already did. That's for the PABA. Okay, I want you to do this guy right here, D. So in this problem, determine the empirical formula. And remember, empirical formula is the lowest ratio of this compound. It contains 62.1% carbon, 5.21% hydrogen, 12.1% nitrogen, and 20.7% oxygen. So it's got similar elements as the last one, but they're in a different percentage. And so I'll give you about 3-4 minutes to get that set up. Great. So sort of similar to the last one, but the numbers aren't quite the same. So in this one, I have 62.1% carbon, and I can assume if it's 62.1% that it's also 62.1 grams, because I take into account 100 gram sample. So this is of carbon. I have 5.21 grams of hydrogen. I've got, I have to write there, 12.1 grams of nitrogen and 20.7 grams of oxygen. So I'm going to divide 1 mole of this value. I'm going to divide it by the molar mass, 12.01 grams. I'm going to divide this by its molar mass, 1.01 grams, and this one by nitrogen. Sorry, it's getting so messy here. What is it, 14 grams of nitrogen, and then this one is 1 mole of oxygen for 16 grams of oxygen. Okay, so first step is just to get out of moles. I'm going to erase these so that I can get a little bit more space. So once I have divided each of those by their molar masses, I end up with 5.1707 moles of carbon. Don't round until the end. Keep all the numbers you can. 5.1584 moles of oxygen. I'm liking that these numbers are really similar to each other. I've got 0.8637 moles of this was hydrogen. Nitrogen. And then 1.29938 moles of oxygen. So I need to divide all of these by the smallest number, the smallest or decimal, which would be this thing right here, this 0.8632. So we're going to divide all these by 0.8362. And my values end up becoming 6 for the first one, 6 for the second one, 1 for the third one, because anything divided by itself is 1. And then the last one is 1.5. So in this problem, we have to do one more step, right? So we get percent into grams, grams we convert into moles, we divide by the smallest number and hope that we're going to get whole numbers. In this case, we got all whole numbers except for 1. So the best way to get rid of that is to multiply it by some whole number. So I need to multiply it by something that's going to get rid of the 0.5. What do we multiply 0.5 by to get it to a whole number? 2. Okay. What do we multiply 0.33 by? 3. What do we multiply 0.25 by? 4. What do we multiply 0.2 by? 5. What do we multiply? So on and so on. Okay. So in this case, we're going to multiply it by 2. So that multiplication gets distributed to everything. So 6 times 2 is 12, 12, 2, and then our 1.5 times 2 is going to be 3. So in the end, we end up with carbon 12, hydrogen 12, nitrogen 2, and oxygen 3. Any questions on how to solve that? There are some more example problems, that you guys can work on your own. They have their own, they have answers to them. So feel free to go through that. Any questions? Okay. Next thing that we're working on is sort of ties into this anyway, so we can get a little bit more practice. Talk about molecular formulas and how to determine a molecular formula. So all the formulas that we've found so far have been empirical formulas. Empirical formula meaning it's the lowest whole number ratio of the atoms. A molecular formula is some sort of multiple of the numbers of the empirical formula. If we find the empirical formula and we know the molar mass of the molecular formula, we can find the molecular formula pretty much just by dividing them. So if I have, let's say I have HO is my empirical. A molecular for this could be H2O2. How do I get from here to here? I have to multiply by 2. This number here is known as N. N is going to be your molecular mass divided by your empirical mass. On problems, this will be given. Okay, this you'll have to calculate from the empirical formula. So N, or your multiplier value, is equal to the molar mass of the molecular formula divided by the molar mass of the empirical formula. Or like, how many times bigger is this thing from this? This thing is twice as heavy as this, hence why you give it a value of 2. So if we look at a problem here, the empirical formula of a compound was found to be CH. Okay, so you know the empirical formula is CH. It has a molar mass of 78 grams per mole. Anytime they're giving you molar mass, this is the molecular formula's mass. What is the molecular formula? So in order to find the molecular formula, I need to know what my value N is. N is how much bigger is my molecular formula from my empirical formula. So N equals molecular over empirical. And so in this case, I've got 78 grams per mole is my molecular, because again, that number is always going to be given to you. And then I need to figure out the mass of my empirical formula. Well, my empirical formula is a carbon, which is 12, plus a hydrogen, which is 1, so 13. So we get an empirical formula of 13. So we put the 13 on the bottom. Then we take our 78 and we divide it by 13. 78 divided by 13. And I get a value of N equals 6. But I'm not done yet. This is just the multiplier for my empirical formula. In order to calculate that molecular formula, I need to actually plug it in. So I take my CH and I multiply it by 6, which goes C6, H6. Obviously, if there was some subscripts on there, we would need to multiply those by 6. Any questions on that? The slides don't give you this formula here, so have that accessible somewhere. Your N value should always be a whole number, so it should always be the bigger number divided by the smaller number. So if you forget, oh, what's the molecular, what's the empirical, you're gonna have 2 numbers, make sure the bigger one's on top. Okay, let's do a couple of these. If I can ever escape my slides. We don't want to do combustion analysis just yet. All right. So the molecular formulas are telling us what actual number of atoms are in the compound. It's some multiplier. So what is the molecular formula for a compound with an empirical formula of HCO2 and a molar mass of 90 grams per mole? So anytime you want to get your molecular formula, you need to solve for that value of N. Okay, so when solving for molecular, you always need to find that N value, that multiplier value. So put the molecular mass over the empirical. Molecular will be the one given to you. So whatever is the mass that's written in the problem, that's the one you're going to put on top. So we've got 90.0 grams per mole. The value on the bottom, the empirical, you have to get from calculating the empirical formula mass, right? So I need to take hydrogen plus a carbon plus 2 oxygens, which is 45 grams per mole. I can see here, okay, this is going to be a relationship of 2 to 1, right, or twice as big. So my N value is 2. You don't just stop at the 2, though. You need to take the original formula, CO2, or the empirical formula, multiply it by 2. So that's going to give me H2C2O4. So this is what the lowest ratio is, but this is what's actually happening in real life. The real molecule itself is 2 hydrogens combined with 2 carbons combined with 4 oxygens. Let's do this one real quick. So we have, what is the molecular formula for a compound? The empirical formula is C2H4O2, and you have a molar mass of 88 grams per mole. So we solve for N. We got our molecular over our empirical. Molecular is given, 88 grams per mole. Empirical is needed to be calculated. So 2 carbons plus 4 hydrogens and an oxygen gives us about 44 grams per mole. Again, it's a similar ratio here. It's twice as big. So we plug it in. C2H4O, we're going to multiply this whole thing by 2, which will give us C4H8O2. Any questions on molecular formula? I think this is a little bit easier than these. It's at least less steps. Okay, but you don't want to be using this when you're solving for molecular and vice versa. You don't want to be using molecular stuff when you're solving for empirical. So a real life application to these things is when we do a combustion analysis. So here's a picture of a combustion analysis. So I've got a sample of some sort of like hydrocarbon. We could say that it's, I don't know, some sort of carbon, hydrogen, oxygen mixture. It could be like inorganic material. Maybe it's like part of an apple or something. And what I can do is I can pump oxygen in there and then I can combust it or light it on fire. And what it will release, because it's a combustion reaction, is we're going to get H2O and we're going to get CO2. And we have two receivers that will absorb or trap each of those. So if I know the mass of my original sample, and I know the mass of the collected water, and I know the mass of the collected CO2, I can actually calculate what it is that that apple's formula is. How do I figure it out? Because I'm not given, I'm given water and I'm given CO2. I'm not given hydrogen, carbon, and oxygen. So how do I get my carbon value? Well, because normally, I'd give you, oh, it's 15% carbon. But if I don't give that to you, you can figure out the mass of carbon if you know the mass of the CO2 produced. Right? So carbon is being determined by your CO2 produced. Okay, so we go from the CO2 to get our carbon value. Hydrogen, we are figuring out from the water produced. So water tells us something about our hydrogen. Oxygen, we don't get the oxygen value from the product. Why? Because we've actually added oxygen to the system, so that number wouldn't be correct. So we would actually take the value of our sample, subtract the carbon that we calculated, subtract the hydrogen, and then we can get the amount of oxygen that's in the original sample. Once I know my grams of carbon, grams of hydrogen, and grams of oxygen, I can then go through the process of figuring out my empirical formula. Let's do one. Why not? It's very similar to what we did in the last problem, but adding just another element at the start. So how do we get carbon from our CO2? Well, if we know the mass of the CO2 produced, we can figure out the number of moles of CO2 produced, right? Because mass and moles, or moles and mass, are related through their molar mass. If I know the moles of CO2, I know the moles of carbon. Because remember, this formula is a mole relationship. So for every 1 mole of this CO2, I get 1 carbon, or 1 mole of carbon. From there, I can go from moles of carbon back into mass of carbon really easy by taking the molar mass of my carbon. You may want to have this flow chart written down somewhere when you're dealing with combustion analysis. So this will get me my carbon values. And then in order to do hydrogen, I do the same thing, but instead I start with my mass of water. I convert it into moles of water, and I'm looking for hydrogen, okay? So for every 1 molecule of H2O, I get 2 hydrogen atoms, or for every mole of H2O, I get 2 moles of hydrogen. That will hop us into just hydrogen. And then from there, I can go into mass by taking the molar mass of hydrogen. We're gonna, we got 15 minutes, so I think we can get through one of these together. We'll do it together. Okay, so I've got a combustion analysis problem. It will say combustion analysis. Come on, man. computer is just not my friend today. Okay, so what is this? Methyl methacrylate has a molar mass of 100 grams per mole. All right, there's one piece of information. That's talking molar mass. That's talking about molecular formula stuff. When a sample of this material weighing 3.14 milligrams was completely combusted, the only products formed were 6.91 milligrams of CO2 and 2.26 milligrams of water. What is the molecular formula? So the first thing I need to do is take my CO2 value and try and get it into grams of CO2. So this gives me the value as 6.91 milligrams of CO2. Right off the bat, I don't like milligrams. I want to get that into grams because molar mass is always relationship of grams and moles. So for every 1 gram of CO2, I will have 1,000 milligrams. That's the relationship of CO2. So I've let go of milligrams. Now, going back to that flow chart, I'm in grams of CO2. First step is to get it into moles of CO2. So I know that 1 mole of CO2 is equal to 44 grams of CO2. That's just the molar mass of CO2. All right, when you're doing these combustion problems, it's always going to be CO2 and H2O here. So now I need to do kind of, not really a magic trick, but I want to go from this into something else. So 1 mole of CO2, I want to go towards just carbon, right? And I know that I get 1 mole of carbon in every 1 mole of CO2. Why? Because there's a 1-to-1 ratio, or 1 mole of CO2 yields 1 mole of carbon and 2 moles of oxygen. In this case, we're not even going to use this. We're just using this ratio here. So we've got grams have canceled, moles of CO2 have canceled, and now I'm in moles of carbon. I don't want moles though, I want grams. So I'm going to take 1 mole of carbon for every 12.01 grams of carbon. Because my final answer here is in milligrams, or my original sample mass is in milligrams, I'm going to convert this back into milligrams as well. So for every 1 gram of carbon, I get 1,000 milligrams of carbon. So yes, your dimensional analysis can get very long. But this system is going to be the same for every combustion analysis. So this first one is going to hurt the most, and then they should just sort of feel like a repeat. So at the end of all of this, when I plug this into my calculator, I end up with 1.89 milligrams of carbon. 1.89 milligrams of carbon in that original sample. We have to do the exact same thing, but we're going to do water, and water tells us something about hydrogen. So I have 2.26 milligrams of H2O. All right, for every 1 gram of H2O, I get 1,000 milligrams of H2O. I want to convert from grams of H2O into moles. So 1 mole of H2O weighs roughly 18 grams of H2O. Now this is the important step here, because if you had missed this step, it would have been okay because you're a 1-to-1 ratio. But here, for 1 mole of H2O, how many moles of water do we get? is not 1. Right? How many atoms of hydrogen come out of 1 mole of this? It's 2. So we need 2 moles of hydrogen. So this step right here on the water one is what may throw you off. It's a 2-to-1 ratio. Then from there, all right, for every 1 mole of hydrogen, it's 1.01 grams of hydrogen. And because it's in milligrams, we'll convert it back into milligrams. For every 1 gram of hydrogen, I get 1,000 milligrams of hydrogen. So after this whole guy, we end up with a value of, and you always want to check and make sure that your values are canceling. So in this case, milligram and milligram, gram and gram, mole of water, mole of water, mole of hydrogen, gram of hydrogen, gram of hydrogen. We get 0.253 milligrams of hydrogen. So I have milligrams of hydrogen and I have milligrams of carbon. I need to figure out my milligrams of oxygen. Thank goodness. That is a little bit easier than the rest of them. We just take the mass of our original sample. So the mass of the original sample was 3.14 milligrams. Okay, so 3.14 milligrams. And I'm just going to subtract my carbon, 1.89 milligrams, and my hydrogen, 0.253 milligrams. Okay, and what we end up with is 0. Come on. Sorry, my pen is dying on me here. Yeah, I think my pen may have died on me. Oh, there we go. Okay. So we get 0.997 milligrams of oxygen. So now I have milligrams of carbon, milligrams of hydrogen, and milligrams of oxygen. Now I can start the problem. Okay, so that's the new stuff. That's the new part of it. And that's a little bit of stoichiometry, which we're going to go over more in depth later, but going from one thing to another thing through mole relationships. So now that I have my milligrams of each, I've got what, 1.89 milligrams of carbon. Got 0.253 milligrams of hydrogen and 0.997 milligrams of oxygen. I need to convert my milligrams into grams. So for every 1 gram of carbon, it's 1,000 grams. 1,000 milligrams. Every 1 gram of hydrogen, it's 1,000 milligrams. And for every 1 gram of oxygen, again, it's 1,000 milligrams. Okay, that'll get us out of milligrams. Now we have grams of carbon, grams of hydrogen, grams of oxygen. We just take these and we divide them by their molar mass. So 1 mole of carbon for every 12.01 grams of carbon. 1 mole of hydrogen for every 1.01 grams of hydrogen. And 1 mole of oxygen for every 16 grams of oxygen. Hopefully you're seeing how this ties into the previous problem. We end up with some super teeny tiny numbers, 1.574 times 10 to the negative fourth, 2.505 times 10 to the negative fourth. This is for carbon, this is for hydrogen, and then 6.231 times 10 to the negative fifth. This is for oxygen. So we need to divide each of these by the smallest number. This is the smallest number here. So we'll divide everything by that 6.231. And I end up getting a hydrogen value, or rather a carbon value of equal to 2.5 moles. I get a hydrogen value of 4. And I get an oxygen value of 1. All right, not quite a whole number, so I need to multiply by 2 to get rid of that. So by 2, by 2, by 2, we end up with 5, 8, 2, or C5H2. I'm sorry, C5H8O2. And you're done. Only took us like 20 minutes. Okay, so that is a combustion analysis problem. We will do one more of these on Thursday. On Thursday, yeah. We'll do another one. It's going to follow the exact same system. All right. So first, going from your CO2 values to get your carbon values, going from your water value to get your hydrogen value, subtracting those from the original sample to get your oxygen value, then you get to plug it into that system to find the empirical formula. Any questions on that? Educated questions, not I have absolutely no idea what you just said, but something that's like, oh, where did that come from?
Does it
I'm sorry, what was it? I heard somebody. Can't hear him anymore. Okay, well, we're gonna leave that for today. So we will do another combustion problem on Thursday, and then we'll get to do more stuff too. We'll get to do the limiting reactant. So there's a lot in this chapter. If you have any specific questions on what we did today or any admin questions, stuff, stay around and I will help you out. Otherwise, you are free to go. Bye-bye. Log off as soon as you can so I know who has questions and who doesn't. It's Thursday.